Hello everyone, welcome to this channel. Today we will solve Leetcode 215, which is kth largest element in an array. So we have given an array and we need to find the kth largest element. So there is a note point here which says that the element might be repeated in the array. So we have to find the kth position, not the kth distinct element. Right? Then okay, let me explain with the second example. So over here we have given this array with 9 element and k equals to 4. So once we sort it in the descending order, then our array will be looks like something like this. And then the fourth element from here, this is the first element, the second element, third element, the fourth element will be here. So basically what we need to do is we have to sort the array and the element present at k-1 index, right? K-1 index will be answer for our problem. So the simple approach would be just sort the given array in descending order and find the k-1 index value. So what would be the time and space complexity for this algorithm? So sorting will take n log n, and then finding this is O of 1 step, so time complexity will be O of n log n. And now it comes to space complexity. For that, if you use merge sort, then it will take n time, and so depending on the algorithms used, it depends on the sorting algorithm. Next, let's see how we can optimize further. So if you look at here, we have to find the kth largest element. So what we can do is we can use heap and store only k elements. So just think about whether we need to use the max heap or min heap. So in min heap, basically the max, this is the min heap, right? So the minimum element out of all these will be present here. But if we use the max heap, the maximum element will be present at root. So in this approach, what we are doing is we will use the min heap, which says that and the size of this element would be k only. So the element present at this will be the kth largest element out of these elements. So if we have total k element, so this minimum element, because all the element present below this root will be greater than this. So this is the kth element if the k is the size of this min heap. So what would be the algorithm? What we can do is first we traverse the array and keep on adding into the heap until the heap size is less than or equal to k. And the second case is when the heap size is greater than k, then we have to decide whether we have to delete this root element and add new element or not. So what will happen, let's say at root of this min heap is 15 and new element comes is 10, then whether 10 would be the answer or not? No, because this is already smaller than this element. It means that all the top k element will be larger than this element, so this element will never be my answer. But let's say the new element comes is 20, then this element will be my answer because this is greater than 15 and top k element, this should be the part of top k element. So what we'll do is we'll delete this root element and add this element into the heap. And proceeding further, when we will be able to visit all the elements in the array, then finally the root of this min heap will be my answer. So let's think about time complexity in this case. So what we are doing is we are adding elements into the heap and deleting one element and adding an element in case heap size is greater than k. So, and the heap size is k, so for each element either to add or delete, it will take log of k time. And how many elements we have? Total n element. So this will be the time complexity over here. Just think about the space complexity. So here we are using heap of size k, so extra space would be O of k. Let's think if we can optimize this further. So what we can do here is we can use quick sort here. So basically the idea here is in quick sort we choose the pivot element, and based on the pivot element we partition the given array. So if let's say the pivot element is placed at k minus 1th index, then this will be my answer, because we need to find what is the element present at k minus 1th index when the array is sorted in decreasing order. So we will follow this approach. So what we'll do is we choose the pivot element similar to the quick sort algorithm. This step will be we'll choose the pivot. Next we'll partition based on this, and if this pivot element is present at k minus 1th index, then we have to break this algorithm and we have to return that element as an answer. What would be the time and space complexity over here? So as we know that this is the standard quick sort algorithm, which in worst case would take O of n square time, right? And average case it will take n log n time, right? And if you talk about the space complexity, so space complexity over here is because we are having the recursion call, and which might lead to O of n in case of skewed partition like the inverse case, because it's a recursion and space used in recursion stack is the depth of the tree. So let's see if we can optimize this further. So if you see here, in worst case it is taking n square. So in quick sort, as we know that worst case will happen only if the pivot element resides in such a way that the array got partitioned in 1:n part. Let's say this is n and this is 1. So if you choose a pivot element in such a way that after partitioning it will comes out to be here, and the next again if we have n minus 1 size here, and again it will partition in such a way that the pivot will present over here, and again if you keep on going, then the time complexity for this one will become O of n square. So in worst case the recursive functions would be look like, as you partition in two parts, which is one is t of n minus 1, another is 1, so we can solve one very quickly, and then in partitioning takes O of n time. So this would be the recursive equation for worst case, which comes out to be O of n square. Then what we can do is, just to save this kind of partitioning, what we can do is we can shuffle the array. We can shuffle the array such that even if we have given the worst case scenario, so worst case scenario for the quick sort is if array is already sorted, right? In that case it will partition in n is to 1 format or 1 is to n format. So what we can do is, even if we have given the worst case input, we will shuffle the array and then apply the quicksort algorithm. So first step will be shuffle the array, then apply the quicksort algorithm. So in this case also, this shuffling will take O of n time, and this quicksort will again take n log n in the else case. But here, after shuffling the array, we will know that the given array will not be partitioned, always will not be partitioned in this way. So that's why the time complexity over here is n log n, and the space complexity, as we say, is again going to be O of n. So next, we have other approach as well. That's fine. So here, after shuffling the array, we will be able to get the solution in O of n log n time. Let's see the solution for this first. Okay, so what we need to do is, we have to first shuffle the array. So for shuffling, what we can take is, we can take a random index and then swap it with the current index. So this is the function to shuffle the array, and after shuffling the array, this is the standard algorithm to do the quicksort. We have to partition it, and then based on that we have to choose the partition. For example, in this way, if we find the element at, let's say, kth index, then means we have to decide, either we have to go left side, either we have to go right side. I'll explain by here again. This is not approach 4. What will happen? Let's say in partitioning, after partition, what will happen? This is the array, and you choose a pivot element, let's say this one as a pivot element, and you run the partition algorithm. So after partitioning, the pivot element will move to this position, and this position, and this is the k, let's say. So if pivot element placed over here, then where we can find the kth index? It will be on right side. Okay, so we have to apply quicksort over here only, not in the complete array. Similarly, if next case would be, if let's say this is the array and we choose this as a pivot element, and after partition, this element placed over here and k is here. In that case, we have to run next quicksort iteration from here to here, because k, we need to find the k-1th index, which is over here. So instead of k, I'll say k-1. So if k-1 index over here, then we have to run the quicksort algorithm over here. Okay, so what I did here is, I will just do the partition and find the index where this particular element will be placed. If this particular element is equivalent to k-1, then yeah, we got the element, return it. If the particular element is greater than k-1, so mid is greater than k-1, then we will find the k-1th element on the left side. So we have to call this from left to mid -1, and if not, then we have to call on the right side. Okay. Yeah, so yeah, I was saying there is one more algorithm that we can think of, which will be approach 5. So here what we can do is, as we can see that we are choosing pivot element at a fixed position. So in standard algorithm, either we can take pivot element as a 0th index or n-1 index or any fixed index in our algorithm, and then we run the partition. So we are not sure after finding this pivot what would be the partition. It could be 1:n partition, it will be 30 to 70 partition, it will be 10 into 50 partition, anything. But what would be the better solution? We can take median as a partition. So if you take median as a partition, so median is an element which reside almost in the middle of the array. So in that case, our array will be not partitioned in the skewed fashion. Okay. So what we can do is while choosing the partition element, so the partition element will be the median of median. So I'll explain this median of median algorithm in next video. I'll share the link in the description. So the only change in this algorithm is in quicksort, choosing the partition will not be done statically. Instead of that, with the help of median of median algorithm. Okay, and this algorithm will run in O of n time and O of n space. Okay, so I'll show you the code as well. So here, just the only change is instead of choosing the pivot element randomly, which we were choosing in this over here, yes. So here we are choosing pivot element as the last element, but here instead of the last element, we'll choose the median of median element. And I will explain this median of median algorithm, how it works, everything in the next video. Okay, thanks for watching this video. For any doubt, query or suggestions, just write into the comment section.